All right. So now some of this information we would have covered already, but we're going to go in a little more detail. So introduction to TCP/IP, transport and application. Right. So we're looking at the layer 4 protocols, TCP and UDP. How
Yeah,
these
yeah.
are functions. So multiplexing using port numbers. What you mean by multiplexing now is allowing multiple communications to take place between two devices and still have them being separated at the at each device. So, for example, um, as we could use in my case here, I have these 6 tabs open. Each tab with 5 of them going to Google and one going to U-Certify. But they are all web-based. So when they're going over the internet, it's all coming from me. But when they get to me, they need to be separated on the computer. So going over my internet connection, they are multiplexed, and then when they get to the computer, they need to be demultiplexed so that my computer would know which tab to send each one to. So that is going to be done via the port number.
So that's a layer 6 thing?
Four, therefore.
Or layer 4. Okay.
Right. Right. So the next thing we're going to talk about is error recovery. Still at layer 4. So in this case, we're going to be looking at things like the sequence number and the acknowledgement. Flow control using windowing. So we would have talked about it before, but we're going to look at it in more detail now. We're going to talk about the establishment of a TCP connection and the termination of the TCP connection. And we're going to look in detail in terms of the order of the TCP connection. So, like, let's talk about things like um, how does a computer know what protocol is at the upper layer? Alright, so before we start any of that, we must have a very good understanding of the TCP header. I think we would have seen this before, right?
Yes, yes.
Okay. Right. So we have the source port, which is 16 bits, and destination port, which is 16 bits. Then there's the sequence number. Sequence number is 32 bits. Acknowledgement number is also 32 bits. Then the important thing inside this section is the flag bits and window. So the flag bits are a set of 1 bit functions. So, for example, if we're sending an acknowledgement, then there's a single bit inside here for acknowledgement. If we're sending a sequence number for segment, then there's a single bit inside here for sequence number. If we're sending a segment that is to be labeled as urgent, there's a single bit inside here for urgent information. So these are a set of single bits that indicate exactly what the segment is supposed to be doing. We call them flag bits. There are actually 9 flag bits currently. Um, this entire section here, the reserved and flags, are 12 bits in total Currently, 9 of them are user flags and 3 of them are reserved.
So although you're explaining the rest of bits, the 4 bytes at top is just for the 16 bits for the part that I highlight.
Oh no! All right. So this 4 bytes here is
32,
saying
for 32 bits, okay.
right.
Mm-hmm.
So
It's
it's
just the
saying that Brian,
source and destination port.
right. So these two make up
Mm-hmm.
32 bits, but also this
Mm-hmm.
make up 32 bits. So it's saying anything that span this entire length is going to be 32 bits.
Okay, okay.
Right. So acknowledgement number is 32 bits. And if we're measuring all of these, the offset, the reserve, the flags, and the window, that will add up to 32 bits.
Okay.
So the offset is 4 bits. The,
Mm-hmm.
the latest version of TCP have only 3 bits reserved and then 9 bits of flags. So we're talking about 4 plus 3, that's 7, and
Mm-hmm.
9, that's 16.
Mm-hmm.
And then the window is 16 bits.
Okay.
So that will make it 32. The checksum is 16 bits and the urgent
Mm-hmm.
is 16 bits. So that's
Okay.
another 32.
Okay, so everybody add back to 32.
Right.
Okay.
So in terms of the size of the segment, then what we would do is just count these 1, 2, 3, 4, 5. So it's
Mm-hmm.
5 different layers, and each of them are 32 bits. So it's 5 times 32,
Mm-hmm.
which gives us what's that?
Well,
Five,
161.
how much?
160. Or
160.
that's
Yes.
162. No, 161.
Yeah. One. No, that will be 160.
32.
Yeah. Multiply
Yeah,
by
yeah, yeah. Yes. 160.
right. So 160 bits.
Mm-hmm.
And if we divide that then by 4,
Mm-hmm.
so we would get 4 into 16 is 4. So we get
Mm-hmm.
40 bytes.
Yeah.
Um,
Yeah, five. Yeah. 1, 2, 3, 4, 5.
sound,
Yeah, yeah.
they don't sound right though.
Yeah, hold on. Let me see. First one is 32. We got our bytes. All right. First byte 4, 8, 12, 16, 20.
Yeah. So right. So two.
20.
So if this is 4 bytes, is
Mm-hmm.
really 5 4 is 20. It's
Yeah,
20
20.
bytes. Yeah.
But we are arithmetic already.
Yeah. I know something was off.
Yeah.
So it's really 20 bytes. Okay. All right. So let's look at communication now. Right. So we have Hannah and Jesse, and they're supposed to be communicating. Now, Jesse is the web server. Hannah is just a normal client. So it says, I received 3 packets from the same source MAC and IP. Which of my application gets the data in each? Right? So the server needs to know which application to send these 3 set of communication to. So as you see here, as a frame, so this is representing a frame. Let me get my pointers. Right, so what we're looking at here is a frame. Now we know it's a frame because it is encapsulated by Ethernet. So we have Ethernet. beginning and Ethernet at the end. So this is the Ethernet header and this is the Ethernet trailer. Now inside Ethernet we're going to have an IP, which is layer 3. Then we have a layer 4 set of information, in this case UDP, and then the actual application layer data. So as you see, when Jesse gets it and Jesse begin to de-encapsulate the frame, once the Ethernet section is taken off, what Jesse will see is the IP, is layer 3, so it will see the IP address. In fact, if we go back to Ethernet, at the Ethernet layer, what is going to be seen is the MAC address. So the Ethernet is de-encapsulated. So take out that, what is seen next is the IP address. Then when the IP section is removed, and now bring it up to layer 4, at that point, the Jesse will see UDP. And then when UDP section is removed and the information is taken up to the application layer, then the application data is seen. So that's how it works. And so in that way, Jesse, which is the server, is able to now recognize the different applications. With me?
Yes.
Okay.
Mhm.
Alright, so let's build out a little more detail inside of this. Same two computers communicating. But now we are saying that the first application is a web server. So that's going to be using port 80. Then we have an ad server using port 800. And then we have some kind of wire application using port 9876. So for the ad application, at the UDP section, inside there, there's going to be a destination port that indicates port 800. Now, port 800 is actually identifying the application. So we know that it is that application that is using port 800. Similarly, for our wire application, in this case, it's using TCP. Port number is 9876. So we know now that this wire application is using port 9876. So when Jesse gets it, Jesse is able to tell which application should get the content based on the port number that is seen at layer 4. Make sense?
Yeah, yes, actually, I read that so it happened.
So, so this is where we see the multiplexing happening. So on the wire we'll have these three sets of information. But at, when it gets to Jesse, Jesse can easily separate them by just looking at the port numbers in each piece of communication and know where to send it.
Are we required to remember those phone number?
Um, yes, not these in particular.
Okay.
Right, these are really being used for example, but port numbers generally yes. So
Mm-hmm.
the ones we call the well-known port numbers, like
Okay.
port 80 for
Mm-hmm.
web,
Yeah, yeah.
port 443 for HTTPS,
Mm-hmm.
port 25 for SMTP, um, port 110 for POP3, port 21 for FTP, port 69 for TFTP. So those port numbers you definitely will need to remember. Right, so here is the same communication but broken out now in further detail. So Hannah on the left, Jesse on the right. We start with the add application. So notice here on Hannah's computer, the add application is using port 1025. And this typically will happen on the client. The port number that is going to be used will be a port number that is above 1024. It's usually the higher port numbers because these are what we call the dynamic port number. So the client will just simply pick a port number to initiate the communication. But at the server, the port number is going to be fixed. Now, just to make sure that is clear, if HANA closes connection and start a new one with the same add application, the port number may not be 1025 again, it may be 1090, but it will always be 800 over on the server. So the port numbers on the server are going to be fixed, but at the client, it's dynamic. Every time the communication starts, the port number could change. That makes sense?
Yes, I understand.
Right, good. So as we see here now, um, we see Hannah. This is Hannah's IP address. Hannah is using UDP, and Hannah's port number, source port number is 1025. When that information is sent over, it's going to Jesse. Jesse's IP address is 10.1.1.2, still UDP, and the port number is 800. So when Jesse receives it, Jesse knows that it should send to whichever application is using port 800. Looking at the wire application, so again, Hannah will just pick a port number dynamically, and in this case it's 1028. So we see Hannah's IP address, TCP, source port number 1028. It goes over to Jesse. Port number on Jesse is fixed, so it is 9876. So again, if for some reason this connection is closed and Hannah is starting a new connection, port number may not be 1028, it could be something else. But on the server, it is always going to be the same. That will never change. Alright?
Yeah, yeah.
So here are port numbers now that you definitely will need to remember. 20, which is FTP. FTP actually use two, 20 and 21. 20 is for the data, 21 is for the control. SSH use 22, Telnet 23, SMTP 25, DNS 53, and so on and so on. You will definitely need to memorize this. So looking at starting a connection now. So we have start with a SYN. Right? All connections start with a SYN, synchronization. Then, so in this case, the client sends a SYN, server responds with a SYNACK, and then the client responds with an ACK. Once all three of those segments are set, then a connection has been established. During that process, the devices will identify which ports they are using for the communication. So notice the web server, the client via the web browser would have identified that the port on the server is port 80, and this is the port on the client. Um, and the synchronization says I would like to start a communication. The server will respond with a SYN which says, okay, I am agreeing to start the connection. And the acknowledgement is saying, I have received your request to start. Right? So the ACK is really an acknowledgement. I have received your request. And the SYN saying, yes, I want to have a communication with you as well. So the SYN really indicates the starting of something, and the acknowledgement indicates a recognition of something. With me?
Yeah, yes.
Right. So the last step is where the client now acknowledges that the server wants to also communicate. So it has an act here.
I elaborate on the D port and S port, man.
Oh, so D port is the destination port. So the server is saying,
Mm-hmm.
not the server, the client is saying, the port I am sending to is port
Mm-hmm.
80.
Mm-hmm.
And the port I am using, so the client is saying the port I am using is the 49155.
Okay.
Right, so it sends that information to the server. The server then would have recognized that the client is using 49155. So every time the server needs to send to the client, the server needs to make sure it sends it to the destination port of 49155.
Mm-hmm.
And of course, the server is using port 80. Right?
Mm-hmm.
So this port 80 is fixed. Right?
Yeah,
That
yeah.
won't change. And then in the acknowledgement now, the client is simply acknowledging this request from the server, and
Mm-hmm.
it is using the ports that they have already negotiated on.
And this is similar to telecom, the three-way handshake.
Well, this is the three-way handshake.
Okay, okay.
Yeah. So when we talked about the three-way handshake, we wouldn't have previously looked at the detail. We would have just said is a SYN, then a SYNAC, and then an ACK.
Right, I remember that. Mm-hmm.
Right. Now we're actually talking about the detail that takes place inside of that three-way handshake. And just to let you know, there's even more detail of things that happen during the three-way handshake, which we'll see coming up shortly.
Okay.
We're just doing it piece by piece.
Mm-hmm.
Yeah. So in the closing of the connection now, this is what we see happen. The the whoever and in the any one device can close the connection. And it could be the client or the server, it doesn't matter. Any one of them can close the connection. So in this case, you notice we just have PC and PC because we do not want to let it look like it's only one of them could close the connection. So in this case, the PC on the left is closing the connection. So the PC on the left sends an acknowledgement and then a fin. The acknowledgement is for whatever it had just received. And the fin is saying, I would like to close the connection. The fin for finish. The PC on the right then sends an acknowledgement to say, okay, I understand or I recognize that you want to close the connection. The PC on the right will then also go ahead and send further acknowledgement and then a thing to say, okay, I am closing on my end as well. And then the PC on the left will send an acknowledgement. So both ends are now closing the connection. With me?
Yes.
All right, so we've looked at the starting and we've looked at the closing. What we're looking at this slide is the actual communication now. So not this, in other words, the middle section. So we looked at the start and the end, and now we're looking at the middle section. This is when data is being sent. So the web browser is sending information up to the server. So this would be an upload. So the client sends 1000 bytes of data, right? And it uses the sequence number to indicate how much data is being sent. Right? So a sequence number of 1000 indicates that it's 1000 bytes being sent. Now notice it sends 3 sets of 1000 before there's an acknowledgement. This can be done because of several things. One of them could be during the three-way handshake, they could have negotiated that the server can take up to 3000 bytes at a time. Right? So the server has enough memory space to be able to accommodate 3000 bytes. And in that case, when the client is sending, the client doesn't wait after each send to find out if the server has received it. The client just send the first 1000, second 1000, and the third 1000. And at that point, it would have gotten to the maximum amount that the server can handle based on what was negotiated in the three-way handshake. So the client would then pause and not send anymore and wait for the server to acknowledge that it has received that and can actually take more. So in this case here, this is where the server is saying, okay, I have received all 3000, right? And then it's saying it's going to send an acknowledgement, and the acknowledgement will have 4000, which is saying send me the next 1000. With me?
Yes.
So here we're looking at a case now where um, same situation, but there are some errors. Right? So the browser is sending the 3000 bytes, right? 1000 at a time. So it sends 1000, then it sends the next 1000, takes it up to 2, sends the next 1000, takes it up to 3. But notice right here that in the second send there was an error. Something happened on the side close to the server that caused this second set of 1000 to not get to the server. So the server would not do anything if it doesn't get the second 1000. Right? It doesn't do anything right away. It waits until it gets the byte that takes it up to 3000. And at that point now, it says, okay, I note I have received the first 1000 and I have received the third 1000. What I did not get the second 1000. So it will now send an ACK for the second 1000. You notice in this case the ACK is for 2000.
Yeah, yes.
Right. So once it sends that ACK for 2000, the browser then now would say, okay, um, I need to resend that second set. And so it sends the second set. And when it sends that second set, it waits. Right? Notice in this case, it is not sending three sets anymore. Right? It is just sending just the one set that was missing. Now, once the server received that, the server would have recognized that it now gets the second set, but it knows it already has the third set. So in that case now it says, okay, send me the next set starting from 4000. Make sense?
Yeah, yeah.
Alright, so what we're looking at here is how the acknowledgement works. Now, remember, I talked about that during the three-way handshake, the devices would have negotiated how much information they can receive at any one time. That amount of information is called the window. So when the server says it can take 300 bytes before it has to pause, right? That is called window. So it has a byte size or a window size of 300 bytes.
3000, 3000.
3000, my bad, right?
Mm-hmm.
Yeah, a window size of 3000 bytes. So um, this is this is what would have happened during the negotiation, right? It would have sent a window equal 3000 to say my window is 3000, right? And then the client now would know that when it's sending, it can send, if it has enough to be able to send one big set of 3000, then it could. But in this case, it is sending three different segments going up to 3000. So note it doesn't pause between these 3000. Between each 1000, it doesn't pause. It just sends 1000, another 1000, another 1000, because the server has indicated that it can take 3000. Now, once the server gets the 3000, the server then would now send over an acknowledgement to say, I have received that 3000, and you can start send the next set. But in this case, what we're looking at here is that the server has now increased its window size. So in responding to say send the next set, the server also include a new window to say send me the next set starting at 4000, but please note my window size has increased to 4000. So when the client is going to be sending now, the client is going to send four sets of 1000 because the server has indicated that its window size is now 4000. That makes sense?
Yeah, that's for the question what you answered.
Okay.
Yeah.
All right. So that's TCP. Now UDP is not that reliable, so it doesn't have all those acknowledgement and sequence number and so on. Right? So typically what happens with UDP is that UDP would watch to see what TCP does and just use whatever TCP is doing. So if during a communication TCP says I have a window size of 3000, UDP just use that, as UDP has no way of negotiating the window size. and that's what we're seeing here. All it has is the source port, destination port, the length of the segment, and the checksum. But it has no way of telling, negotiating things like window size and source port and destination port. It doesn't know how to negotiate those. All right, so taking a more detailed look at um, what how we indicate as humans the the information or the destination that we need to get to. Now we are
Okay,
accustomed.
hold on, Lloyd, hold on.
Yeah.
Before we move on, the TCP and UDP, I think I'm trying to remember. You said because the UDP don't make any error check it quicker than the TCP.
Yes.
Okay, and it's not use a voice over IP.
UDP.
Yeah.
Yes, UDP is used for voice over IP.
Okay, so when a bit lost, it just lost then.
Yes.
Okay, okay. Just trying to remember. All right.
Right. And the reason for that is, if we're using TCP,
Mm-hmm.
TCP would actually resend the information.
Okay.
But what may happen is that when the information, well, not may, what would have happened when the information is resent, the device wants
Mm-hmm.
to wait to resequence the information.
Mm-hmm.
So you get some unnecessary gaps in your communication while the
Okay,
device
yeah.
is waiting to resequence.
Yeah. Yeah, I remember now.
All right. So you may be very familiar with the term URL, Uniform Resource Locator, which we typically use with our when we create a link. It is what we call a URL. But a URL is a subset of a larger term, and the larger term is URI, which is Uniform Resource Indicator. So that's the URL, Uniform Resource Indicator. Now, this term is really saying how do we indicate what resource is being used. It has several parts to it. So it has a scheme, the authority, and the path. So the scheme is what tool or what application is being used during that communication. It has a section called authority, which is saying um, who is responsible, alright, who or what is responsible for this communication. And then the path is the actual location where the communication is going to. So this is what we use when we talk about URI. Now remember I said the URL is just really a subset of the URI. So the URL really refers to like websites, links that we use to get to a new web page. Now in that case, we have a protocol. So the URL would have a protocol. It could be HTTP, could be HTTPS, it could be FTP, right, whatever the protocol is. And then the authority, that is the device that is giving authorization for such communication, is the actual web server. Right? Like in this case, the web server being searchskills.com. And then the path is going to be the actual page on that web server, because a web server could have multiple pages. So we're saying where on that web server should the information be sent to, or should the request be asked of. Make sense?
Yes, sir.
Alright, so DNS. Now we'd have talked about DNS as well, but we're going to again look in more detail. So volume 2 is really about getting into much more detail of the things we would have talked about in volume 1. So um, we know that DNS is really a way of getting an IP address when we already have a name. So we're resolving a name to an IP address. Right? You're good with that part, right?
Yeah, yeah.
Okay. Alright, so what we have on screen here is a four-step process showing the DNS resolution process. So here's the client. This is the DNS server. And over here is the actual web server that the client needs to get to. So we're seeing three different entities: the client, the DNS server, and the web server that the client needs to get to. So let's look at the process now. So the client in the browser will have typed http colon www.cisco.com/go/learning network. Now, this has to be identified by an IP address, but the client doesn't know the IP address. So the client is going to ask the DNS server what is the IP address. So this section right here is showing us the client asking the DNS server. So notice here now the client is sending the information to a destination port of 192.31.7.1. That destination, and I said port, or destination IP address I should have said. That
Yeah.
destination IP address is the IP address of the DNS server.
Mm-hmm.
Right? And then we have the source IP address, which is the IP address of the client. Then the client is using a source port of 1030. Remember, we said the client port is going to be dynamic. The client just simply pick a free port that is available.
They say over 10, 24.
Correct.
Mm-hmm.
The destination port now is what is fixed. And in this
Mm-hmm.
case, it's 53. It's fixed because DNS use port 53. So the client is sending to port 53. And then over here now is the actual request that the client is sending. So the client is saying, what is the IP address of www.cisco.com? Right?
Mm-hmm.
All right. So the DNS server needs to respond now. So the DNS server is going to respond to the client. So it is going to use whatever the source IP address that it had received, it's going to use that IP address as the destination IP address. So that's 64.100.1.1. And then the server will put in its own IP address as the source, which is 192.31.7.1. The server will put its own port number as the source port, 53, and then whichever port number the information had come from, that is going to be used as the destination port number. And the server will now include the answer. We say the IP address is 198.133.219.25, which is the IP address of the actual web server.
Okay. That's where that come from.
Okay, yeah, so that's the actual web server. So that would have been
Mm-hmm.
inside the DNS. The DNS would have that in its table.
Okay.
So now that the client gets that information, the client will no longer be talking with the DNS server. Right?
Mm-hmm.
It's going to now attempt to talk directly with the web server. So it is going to create a new set of frames with a source IP address of still the client, but the destination IP address being the web server. And the source port, notice it has a different source
Mm-hmm.
port now because
Mm-hmm.
it just dynamically pick a source port. And the destination port being 80, in this case 80 because it's a web server.
So this will be like same layer communication.
Yes,
Okay.
right. And then of course
Uh,
it's a SYN because it's attempting to start the communication with the
mm-hmm.
web server. So this is the starting of the three-way handshake with the web server.
Yeah, yeah, yeah.
Right. No,
Hold on. Port destination 8. Okay.
notice we didn't have any SYN and SYNAP
Yeah.
with the DNS server, and that's
Right.
because DNS is using UDP.
Mm-hmm.
Right.
Oh yeah. So it's switch to TCP
Right. When it's going to the web server.
web server. Okay, okay.
Make sense?
Yeah, yeah.
All right. So what we looked at over here is a simple DNS request and response, right? But it is not always that simple. So what we're going to look at here is a more realistic situation that happens with DNS,
Right.
and we call this a recursive DNS lookup. Now, this more realistic situation I'm talking about here is that in many cases, the DNS server that the client contacts really does not know the IP address of the web server the client needs to get to. And so that DNS server has to refer the client to a different DNS server. So normally the the client knows only of its local DNS server. So for example, um, at home, our client computers at home, the only DNS server it knows of is either our service provider DNS server, or it is using our modem as a DNS server. Either of those is considered local because um, our service provider is in like still just a part of us. In other words, our computer will not know the DNS server of Google or the DNS server of Yahoo or the DNS server of any organization. It only knows of the DNS server from the service provider or the modem that you have at home. And the same thing in an organization. So, for example, if you go inside Digicel or inside Flow, then the computers that the member staffs our staff are using will only know of Digicel DNS server or of Flow's DNS server. They won't know any other DNS server. So anytime they need to get a DNS name resolution, they would have to first talk to their local DNS server. This way?
Yes.
Okay. Now the other thing is for the local, and this is the local server now. Right? It is listed here as enterprise DNS. This is the local server. This local server, when it is first configured, it will not have any information about any place. So this local server will not know where Yahoo web server is. It will not know where Google's web server is. It will not know where Netflix web server is. It doesn't know anything. The only thing it knows by default is something called the root hints. Right? So listed here as root DNS server. Right? The full name is really root hint DNS server. Hint as in HINT. So all DNS servers are configured by default with the root hints, so they would know how to find the root hints or the root DNS servers. So when we send a request to our local DNS server, because it doesn't know anything else, it is going to then forward that request to the root DNS servers. Right? Good so far?
Yeah, it's just a garbage truck outside and pure nice.
Okay. Alright. Now these root DNS servers, they don't hold individual website information. So they will not know where marketplace.com is or where teletinstitute.com is. They don't hold that information. There's just too many websites around for them to hold all of that information. So what they do, they only keep information of what we call top level domain DNS servers. So the top level domain DNS servers are DNS servers that handle um, the what we call like com, net, um, gov, right? Those top level DNS um, names, right? Now, so these are actually DNS servers as well, right? And the root DNS server only knows how to find these DNS servers. So the root does not know how to find actual web servers. It only knows how to find the top level DNS servers. So
Okay, hold on, lad. Before you go any further, the enterprise DNS server sits in telco, right?
yes,
Okay, that's
or
so.
in an organization. So like
Or
they
an
say
organization, okay.
if we work at let's say BNS, then it would be inside BNS.
Okay, good, good. All right.
So when as a client we send a request for a name to be resolved to an IP address, that DNS server does not know it, so it sends it to the root. The root itself does not know it either because the root does not hold information for individual websites. Root only hold information for top level DNS servers. So root would know where to find DNS servers that can handle anything ending with com. It knows how to find DNS servers that can handle anything that ends with net. It knows how to find DNS servers that anything ending with that handles requests ending with gov, and so on and so on. Right? So if the client had asked for, let's say, Cisco.com, then what the root would do, it would send back to the enterprise and say, I don't really know where Cisco.com is, but I can tell you of a DNS server that knows everything about things that end with .com. Right?
Yeah, you know.
Right. So it will send back now and says, here's the IP address of a server that knows everything about websites ending with .com. And so this DNS server now would have to now put in a new request, right? that goes out to the .com web server, DNS servers, and say, okay, you are the .com, so you should be able to tell me where Cisco.com is. Now, this .com server may not know where Cisco.com is, right? But it knows where the DNS server that Cisco is using is. So what it does now, it sends back to the enterprise DNS server and say, I don't know where the web server called Cisco.com exists, but I know of a web server, of a DNS server that knows that exact information. And that would be the DNS server that is owned by Cisco. So it sends back to the enterprise and says, here is the DNS server that is owned by Cisco. And then now this enterprise DNS server can go to the DNS server that is owned by Cisco and says, tell me where I can find Cisco.com. Since this is owned by Cisco, then it will know where Cisco.com is. So it sends back to the enterprise now and says, here's the IP address for Cisco.com. And it is only at that time that the enterprise server now would actually respond to the client and say, okay, I found the information. Here is the IP address of Cisco.com. That makes sense?
Yeah, yeah.
So as you see, it's a lot more involved than what we had over on this slide here. But that is what would normally happen. Now, after a while though, what's going to happen is the enterprise server has a little area in memory called a cache. So it will save the information for Cisco.com. So it will say, okay, Cisco.com is that IP address, let's say 1.1.1.1, and it save that in the cache. So that if 5 minutes later a different client wants to go to Cisco.com, this enterprise data server can then look in its cache and say, okay, I already have that in my cache. I don't have to go through this entire process anymore. I can just use what is in the cache and send that to the client. With me?
Yeah, yeah.
Alright. So what we're looking at here now is the client would have gotten the IP address of Cisco.com. So it can now communicate with Cisco.com. So we are bypassing the three-way handshake, right? We're taking it now for granted that the three-way handshake has already been done, right? So this is where it is just going to be asking the web server for some data. Because
Mm-hmm.
typically that is what happens when a client communicates with a web server. Right? In
Yeah.
most cases, the client is saying, give me some data. So the client sends www.cisco.com go/CCNT, which is saying, give me the web page for CCNT. So it sends that in what is called a GET message, a HTTP GET, which is saying, let's get this information. So it sends that to the web server. The web server now will, before it actually sends the information, it sends out an acknowledgement to say, okay, I am acknowledging your request. However, under HTTP lingo, it is not called an acknowledgement, it is called a OK. So this OK is like an acknowledgement, right? That HTTP OK. In fact, the full name is HTTP 200 OK, like 200 OK,
Mm-hmm.
right? So the web server would first send the acknowledgement, which is the HTTP 200 OK, to the client to say, okay, I've received your request and I will begin to process that. The client could possibly wait, or the client can still ask for even more information at that time. So in this case, we are seeing that the client is asking for more information. So the client now sends another get and says, send me now the graphics. Under the graphics page, a subpage of logo 1. So they're trying to get the logo. Again, the oh, I missed something here.
Yeah.
Yeah, let's go back up here. Because what I had missed is that they actually included the data with the 200 OK. It is sometimes separated, but they are showing both together here.
Mm-hmm.
So the server sent the HTTP 200 OK, but it also includes the data, saying that one sending, it has the acknowledgement and it has the actual data. So the client would have gotten the acknowledgement and it would have gotten the data for the CCNA page.
And that part will be completed.
Right. So it would have now
Okay.
gotten that information. Now this is another request that is sending out now. It actually wants the logo. So
Okay, good.
so the client is now asking for the logo. And then again the web server would send the acknowledgement and the actual data that has been requested.
Mm-hmm.
Now I want to be clear here that they are showing these two together, the
Mm-hmm.
acknowledgement and the data. It is not always together. Right? Some
All right.
documentation will have them separated.
Okay.
Right. So the client now gets the logo, and the client here is asking for a new request. HTTP get slash graphics slash add one dot gif, which is another image. Right? So anything with GIF is an image. And
GIF.
the server responds again to the 200
Where
OK,
is
which
that?
is,
Where
sorry,
is GIF? Where is the GIF?
at the end, dot .gif.
Oh, okay.
Yeah,
Oh, I don't. Okay.
yeah. So it's anything ending with GIF is really an image, just like JPEG and so
Yeah.
on. Yeah, GIF is a type of image format. In fact, I think GIF means graphic image format.
Okay.
Right. So here is the client asking for a new um, request, and then the server responding HTTP 200 and the actual data, which is the image. All right.
Yeah. Yes.
Okay. So in this case now, um, we want to answer the question about the multiplexing, right? So it is being painted in a scenario here called a dilemma, right? And the dilemma is how host A chooses the application that should receive this data. So this is like your computer now, right?
Mm-hmm.
The information coming into your computer, how your computer know which application should get the data. Because you might have several applications open. So
Mm-hmm.
how your computer know which of all those applications should get the incoming data. And this is how it knows it, right? So your computer is going to get a frame. So the frame is going to be an Ethernet frame. Now inside that Ethernet frame is the MAC address of your computer. So that is how your computer knows that it should accept that frame because it sees its own MAC address. Once your computer strips off the frame and local, it will see the IP address. Again, if it sees its own IP address, then it knows that this packet is for it. Then your computer will strip off the IP section and look now inside the TCP or the transport layer section. Inside there, it's going to see a destination port. That destination port is what tells the computer, tells the receiving computer which application should get the information. Does that make sense?
Yes, it does.
So we're seeing here several um, applications open. So notice these are browsers. So these the first three could be three different tabs in your browser. And then we have email, some email application, and then some chat application. It could be like Skype chat or Google chat or whichever chat function you're using. Now, the client in setting up all of these would have selected dynamically a port number. So when the server responded, the server would send the information to each of these port numbers. So these port number now would have been tied at the client to a specific application. And that is how the client knows now which port number, which application is to get the actual data. Make sense?
Yes, yes, it does.
Alright, so delving into a little more detail. So the same thing that I just talked about here, but we're just going to add a little more detail to it.
Mm-hmm.
So we indicated that the client will look inside the internet frame and see its own MAC address and knows that this frame belongs to it. But the client will also need to know what should it expect at layer 3. How it would know that is inside the Ethernet frame, there is going to be a code that tells the computer what protocol to expect at layer 3. Right? That code is going to be found inside the section called type. So the Ethernet frame will have a section called type, T-Y-P-E. Inside there, there's a code. And that code indicates what protocol is at layer 3. If the code is 0800, and well, it says here 0x0800, but the 0x at the beginning just means hexadecimal. Right? So the 0x means hexadecimal. So the code is really 0800. You understand that?
Yeah, yeah, I remember. Mhm.
Right. So 0800 means IP version 4. If it was IP version 6, it should have been a different code.
Yeah.
Then once the computer gets to the IP section now, then there's a thing called the protocol number. And the IP version 4, well, the IP header will have a section called protocol. And inside there, it will indicate the protocol number. That protocol number will tell the computer what to expect at layer 4, whether to expect TCP or UDP. So 6 is TCP. If it was UDP, you would see Now I'm going to have to pause here because I can't just give you a one number if it was UDP, right? So the number could be written as either decimal or hexadecimal. If it's UDP and it's being represented in decimal, then you'd see 17. So if what is at there for is UDP and we're writing it in decimal, you'll actually see 17. If we're writing it as hexadecimal, then you'd see 0x11. With me?
Yeah.
Right. So whichever one of those you see, 0x11 or 17, it means UDP. Right. Now once we get to layer 4, then layer 4 needs to be able to identify the actual application, and it does that by using the destination port number. Make sense?
Yeah, yeah.
Right.
And I
So
realize this is what you call adjacent layer communication too.
yes.
Mm.
So each layer now has to tell the computer which protocol is at the layer above. I think this is the last slide in this set.
Okay.
So the next thing we're going to talk about here is access control list. Again, we would have mentioned this in one of our previous slides, but to go in a little more detail in these slides. So we're going to look at access control list for IP version 4, and we're going to look at the standard numbered IPv4 access control list. Right, so IPv4 access control list can be used to um, determine what kind of packets you want to allow or disallow inside your network. So you can identify the packet type and make some decision on it. Now, this is usually going to be done at a router. So when you're configuring your access control list, you're configuring it on the router. The access control list allow you to make decisions on packets based on the several protocols. So you can make decisions based on IP, based on ICMP, based off TCP, or based off UDP. And note they say on others. Right? So these are just the more popular ones, but there are other things that we could um, use as the determinant for which packets are going to be allowed or disallowed. Right, so we can use the access control list to to block or allow packets, and we can use it as a quality of service mechanism as well. Now, as a quality of service mechanism, what you can do is you can actually use access lists to send certain traffic to certain ports, and you can actually use it to delay certain traffic. Right? So, for example, your voice over IP traffic, you could ensure that that only goes to the high bandwidth port, or you could ensure that it gets higher priority than your any other type of traffic you have, and that's how to impact the quality of service. With me?
Yes.
Yeah. All right. So, where should we actually put the access control list? That's what we're asking here. Right? And it says locations to filter packets from host A and B going towards server S1. So we have host A here, host B, and the packets are going towards server S1. So where should we filter the packets? Now we could filter the packets right here at the entrance of router 1, or at the exit of router 1, or at the entrance of router 2, or the exit of router 2. So you notice this is only being done on routers. Right? That's where we put our access controls.
Yeah, yeah.
Also notice in our filtering, we will filter it based on the traffic coming in to fast internet 0/0 going in, or if you're doing it on the serial of router 1, you have to filter it based on the traffic leaving the router. If we are filtering on R2, then we would have to filter based on traffic coming in on our serial 0/0/1, or we could filter the traffic based on it leaving fast Ethernet 0/0. So as you see, there's a directional component as well, not just a matter of where, there's a directional component. With me?
Yes, yes.
Alright, so in this case, we are looking at um, filtering on R2, and the filtering is being done on serial 0/0/1, and of course in this case we will have to put it as coming in because it's going into the router at this point. Okay?
Mm-hmm.
So um, the source IP would be the IP address of either PCA or PCB, right? Because that's where it's coming from. And then, well, because we're talking about standard access control list, standard access control list doesn't have a destination. Right? So in the when you're writing the access control list, there's no place in it for you to specify a destination. So you only can specify the source, where it's coming from. Now that is a little problematic for us. Right? And the reason it's problematic, if we, let's say we had put the access control list right at R1 here, at incoming to the router, because we cannot specify a destination, then what we would have just been saying is any packet coming from PCA or PCB and going into the router should be blocked. But that would cause a problem in that the packet might have only been meant to come to R2 and would have blocked it, while we really just want to block things going to the server. With me?
Yeah, yeah.
Right. And this is why with standard access control lists, the rule says you should place the access control list as close to the actual destination as possible. So when you do that now, you reduce the ill effects of the access list blocking things that you didn't want it to block. Alright, so different types of access lists. So we have access lists can be numbered, right, as you see here, or they can be named. So we can either classify them that way, numbered or named. We can also classify access lists as standard or extended. So two ways we can classify them. So we will have standard access lists that are numbered, and standard access lists that are named. We would have extended access control lists that are numbered, and we would have extended access control lists that are named. Good?
Yeah.
Okay. All right. Backdrop for discussion of list process with access control
Hold
list.
on a lie. The pseudo code thing that was on the top there, well, that was the look code that you use. Go back.
Yeah.
That's what you would use
Yeah. Well,
for your
the
purpose. Mm.
pseudocode really means um, writing what we would want to happen in
Mm-hmm.
normal English.
Yeah.
Yeah, so you're not going to write it in a format that the router would understand. So you're not using programming language.
Mm-hmm.
You're using normal English. So that's what this is
Okay.
really saying.
Okay.
So that's just expressing it in a way that
Mm-hmm.
um, any English speaking person would understand.
So somebody access the router with pseudos I know what they're for. Like,
Oh, no, no, no. So pseudocode is not going
mm.
to be typed on the router. Pseudocode is just for documentation.
Okay, okay. I
Yeah,
get it. I get it.
right. So it's just something now. So if you need to talk to somebody and
Mm-hmm.
that person may not be comfortable with the Cisco router programming um,
Mm-hmm.
language, so you write it in pseudocode and it's easy to talk and share information with the person because you and that person both understand English.
Yeah.
Yeah. So that's whenever you see that term pseudocode, that's what it means.
Okay, I get
Writing
it.
programmatic actions in normal English. Okay?
Yeah, yeah.
All right. So backdrop for discussion of list process with IP access lists. Now, so what we're going to be talking about here is this part here, the list process. And it's important because, as the name says, access control list. So when we create our access controls, there's really going to be a list of things, right? So we may have
Mm-hmm.
access control and it may have a number like 5, but 5 is really identifying a list of stuff. So inside 5 there will be a list of things, right?
Yeah, yeah.
Okay. Now, so here is how this thing works now. So if we are putting the access control list on R2 and we are referring it to serial 0/0/1 and it's going to be coming in, we are saying now that in this case, we are saying we want to permit only PCA, right? So notice IP source equal 10.1.1.1 permit. So we're saying permit this computer, whichever source, whichever device has this IP address, we permit this device to send data. Then we want to deny every other device. So IP source 10.1.1.x and x here now then just says it doesn't matter which other device. We are denying that.
Yeah,
Right?
yeah.
And then we are saying here IP source 10.x.x.x. So it doesn't matter the last three octets, it matters not
Mm-hmm.
what they are. We will permit those. Now the the question might come up, right? That says we already permit 10.1.1.1 and we have denied 10.1.1.x, but only 10.1.1. So anything outside of this. should be allowed, right?
Yeah.
That argument may be posed by some persons, but there is something that you have to bear in mind with how routers work. When you start an access list, when you start configure it on the router will always put an entry in the list for you, and you can't do anything about it. The router will always put one entry in the list for you. That entry says deny everything. Right? It doesn't matter which access list you're creating, as soon as you create the list, the router puts one entry inside there. And that entry that the router put says deny everything. The entry will always be at the end of the list. Right? So the router always put its entry at the very end of the list. So if we did not have this, that the entry that the router would have right here would say IP source x dot x dot x dot x, four x's, and it would say deny, which really says deny anything. It doesn't matter what. With me?
Yeah.
So in that case, 10.3.3.3 would not be able to send any information because the router's default entry would have blocked it.
Mm-hmm.
You see that?
Yeah.
So that is
All right.
why now if we really wanted PCC to be able to send, we have to specifically state it, right? And say
Mm-hmm.
IP source 10.x.x.x permit.
Okay.
That would then move the router's default entry down to the end, to entry number 4 at the end, which will say IP source equal x.x.x.x, four set of x's, and we'll say deny,
Mm-hmm.
right? Because the router, we have no control over it. The router will put its own entry. Yeah? We just have to work with it. We have no choice.
Okay.
Now, this also brings up an important thing in that if we're creating an access list, we must always have at least one permit in the access control list. If we don't have a permit, let's say we had created it and the second one here is the only thing we had in our list, right? Then if we had only this, it means the router would still put its entry. And the router's entry would have said IP source equal x.x.x.x deny. So what we would have had is two entries in the access control list, and both of them saying deny,
Yeah.
which means nothing at all could pass through that router. Make sense?
Yeah. Well.
Right. So we have to bear that in mind. We can never create an access control list without at least one permit statement. Good?
Yeah. This one like when I used to bar the speed or some call and turn the cell phone and allow like one and two.
Yes, same
Mm.
concept.
Yeah. Yeah.
Alright. So this showing us based on this pseudocode, what would happen if when the devices try to send information through R2. Right? So that's what we're looking at here now.
Okay.
So if PCA try to send, right? So IP source equal 10.1.1.1 is permit, right? So this would have gone through, right?
Mm-hmm.
All right. Now, and then of course the other statements are not impacted because the next thing we need to know is that let's just come back here. The router, when the router processing any traffic going through it, and it looking at the access list. The router starts from the top of the access list and checks going down, right? So the router
Yeah.
will check here to see if it applies. If it does not apply, it checks here. And if that does not apply, it checks here. And if that does not apply, it checks the default entry, which says deny everything, right?
Yeah. Yeah.
So what we're seeing here now is host A, which is 10.1.1.1, is sending through router 2. The router goes ahead and check and it says, oh, yes, 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 this one is allowed. So let that pass through. So the tick means the traffic will be allowed. Once the router makes a decision on a traffic on that router, whether it be deny or allow, right? The router does not check the other rules, right? So as long
Mm-hmm.
as it is able to make a decision on the traffic, then it doesn't check the other rules. So the ones in blue here are saying the router has not checked it. Okay?
Yeah. Yeah.
Okay. So in this case now we're saying what if host B attempts to send? So host B's IP address is 10.1.1.2. So here host B is checked. So the router looks at this rule that says IP source equal 10.1.1.1 and that should be permitted. In this case, this is not applying to host B. This is, this is applied to a different IP address. So at this point, the router cannot tell if host B should be denied or allowed. In other words, the router cannot make a decision based on this rule. With me?
Yeah.
And remember now, only if the router makes a decision, the router will stop going through the rules. But since the router cannot make a decision here, it has to follow through to the next rule. So it comes to this other rule here now. It says IP source equal 10.1.1.x deny. So it matches them. The first digit is 10, next digit is 1, next digit is 1, the next digit is 2, and the next one here says it doesn't matter what, anything at all that is in this last octet, it should be denied. And it says, okay, so I can't make a decision now, and the decision is denied. With me?
Yeah.
So the router no longer checks, it doesn't check the third one because it was able to make a decision here, right?
Yeah. Yeah.
Okay. So in this case now we're looking to see what will happen if host C was sending. Right? Host C's IP address is 10.3.3.3. So the first rule is checked. The source in that rule is 10.1.1.1. When the router compares the actual PC with what is in the rule, the router says, well, I can't make a decision. Right? This rule does not apply to this computer. Therefore, I cannot say whether the computer should be allowed or denied. So since I cannot make a decision, let's check the next rule. The next rule, IP source equal 10.1.1.x deny. So it checks again. The first digit is 10, second digit is 1. Oh, can't make a decision. Right? Because this rule does not apply to the computer. So the router is unable to make a decision. So the router says, okay, let us go ahead and check the next rule. The next rule now says IP source 10.x.x.x, right? And it says, okay, let's see, 10 matches. The X here says anything, so it matches. The second X says anything, so it matches. The third X says anything, so it matches. So in this case, the router is able to make a decision, and the decision says permit.
Permit.
Good?
Yeah. Yeah.
So that's how the access control list works.
Yeah.
Now we're moving towards now how we would actually write it in the router. So we're moving away from the pseudocode to how it will actually look in the router. Right? Now, normally when you're writing access control list, you would put when you're writing IP address, you would have a subnet mask, right? But in access control list, we actually do not use subnet mask, right? We use something called a wildcard mask. So the WC here is wildcard. So the wildcard mask is written opposite to the subnet mask. So for example, 0.0.0.255 would be the same as a subnet mask that says 255.0.0.0. With me?
Yeah, yeah.
Right? So it's like just switching around the subnet mask. So like this one here, wildcard mask is 0.0.255.255. This is the same as a subnet mask that says 255.255.0.0. Good?
Yeah.
Right. And the last one, the wildcard mask says 0.255.255.255, which would be the same thing as saying if it was a subnet mask, it would have been 255.0.0.0. Alright, so you're seeing the difference there now between subnet mask and the wildcard mask.
Yeah.
Right. So continuing with the logic now. So here we have some IP addresses 10.1.2.0 and 10.1.2.1. Right? The zero in the wildcard mask says the things the octets should match exactly. Right? Anywhere we have a zero in the wildcard mask, we're saying the octets must match exactly. So in this case, 0.0.0.255, we're saying the first octet in the IP addresses must match exactly. Right? In other words, let's come back up here. What we have coming from the device must match exactly what is in the rule. That's what
Mm-hmm.
zero says. With me?
Yeah.
Alright. So if we take the top part to be the IP address of the computer and use the bottom part to be the rule, right?
Mm-hmm.
So we would have said 10, sorry, the zero here means these two must match. Zero here means these two must match. Zero here means these two must match. 255 says it doesn't matter whether they match or not, right? We don't care. We are going to treat it as if they actually match, right?
Mm-hmm.
Yeah. So that's what the 255 is saying. We don't care if they actually match. We are going to treat it as if they do match. And same thing here. In this case, we have 0.0.255. So again, 0 says they must match. 0, they must match. 255, we're saying we don't really care if they match. Alright? Whether they match or not, then we're going to treat them as if they match. In other words, we can simply ignore these last two octets because it matters not what is there, whether they match or don't match. With me?
Yeah.
So 255 is considered as ignore because there's no real reason to be checking them if we don't care if they match. And in this case here, 0.255.255.255, again, the 10, see, they both match. Then over here, they don't match, but we don't care, right? We're ignoring that. We're still going to treat them as if they match. And in this case, top one is 0, bottom one is 3. We don't care. We treat them as if they match. And at the end here, 0 and 4, because we have 255, we're going to treat them as if they match. All right?
Yeah, yeah.
All right. So now we have gotten to what it actually going to look like in the router. So as you see here, syntactically correct ACL replaces the pseudocode. So in other words, we're no longer writing pseudocodes. We're not writing English thing anymore. We're writing the syntax for the router. With me?
Yes, sir.
Right. So this is what the syntax for the router will look like now. So access dash list 1. So we give the access list a number, and then we say permit, and then we put the IP address. So we're permitting this IP address 10.1.1.1 access dash list 1. So it's the same list. This is the top one is the first entry, then this is the second entry, and this is the third entry. And of course, the router will have its own entry down at number 4, right, which is invisible, but it's there, right?
Mm-hmm.
So access dash list 1 deny 10.1.1.0, and then we have our wildcard mask 0.0.0.255. So in other words, we are saying here the first octet must match. So any device that is sending, if the first octet matches, for this rule to apply, the first octet must match, the second octet must match, the third octet must match, but we don't care if the fourth octet match. We'll still treat it as if it's matched.
Mm-hmm.
And for the third one, access dash list permit 10.0.0.0 using the wildcard mask of 0.255.255.255. So the 0 in the wildcard mask is saying the first octet must match. And as you see, the last 3 octets in this wildcard mask are 255s. So we're saying we don't care if the computer actually matches with what is in the rule. It doesn't matter. Anything that is in the IP address for these 3, we'll just treat them as if they match. Cool?
Yeah, yeah.
Alright, one more thing I want to point out on this slide. I go back to the first rule. Notice that we did not put a wildcard mask for the first rule. A wildcard mask should actually be there, but the router will understand if we do not put the wildcard mask.
Okay.
Right. In this case, and the reason why I'm saying it to understand, in this case, the wildcard mask is actually 0.0.0.0.
Oh,
Right? It is 4 zeros. So in other words, we are saying it must match this IP address exactly. Anytime we want to match an IP address exactly, then we no longer have to put the wildcard mask. The computer will understand if we leave it off.
okay.
If we wanted to put it, we'd have to put 0.0.0.0. Cool?
Yeah, yeah.
Alright, so there's another way we could actually do it as well. So when we want to match something exactly, we have 3 ways of writing it. In fact, let me write it down so you see what it looks like. So these are the three ways of writing things if you wanted to match exactly. I'm going to use the example that they have access. So these are the three ways we could write it if we wanted to match exactly. So we say access dash list 1 permit 10.1.1.1 host. Right? Host is saying um, I am not looking at a group of computers. I am talking about just one. Right?
Mm-hmm.
One host. So once you put the word host here, it says I am dealing with just one host. Right? And of course, 0.0.0 is saying everything must match, which brings it to one host, right?
Mm-hmm.
And of course, we could leave it off. So if you leave it off, the computer understands. Or
Okay.
not the computer, the router understands. You don't put anything in the router, just assume that you're dealing with just that one host. With me?
Yeah, yeah.
Alright, so I see it's on 3:05.
Mm-hmm.
So let's go ahead and take our 5 minute break
Mm,
and
all right.
then we start back at 3:10.
Yeah.
Alright.